Right, it's on mute at the moment. So this is the 10.
Good evening, everyone, and thank you for joining us. For those who don't know me, I'm Roger Highfield. I'm the Science Director at the Science Museum Group, and it's my pleasure to introduce tonight's special guest, Sir John Meurig Thomas, and our own chair, Dame Mary Archer. They've got several things in common. Both are chemists, both overlapped at the University of Cambridge, where John was the head of the Department of Physical Chemistry, and both have links to the august Royal Institution, where Mary did her postdoctoral research and John was later the director. And that's one of the reasons why in 1991, John was knighted for services to chemistry and for the popularization of science. Now, we're all fond of the Royal Institution, and that's why, in its honor and to celebrate the spirit of the Friday night discourse, I'm wearing black tie tonight. Now, the term legend is often overused, but there's no better way to describe Sir John, whose long and distinguished career has seen him earn 23 honorary doctorates, notably for his work on catalysis and catalysts such as zeolites. In fact, the mineral Meurigite is named after John. And when he celebrated his 75th birthday with a series of events at Cambridge, they were attended by Nobel laureates and none other than the world's best-known quantum chemist, Angela Merkel. And I should add, his CV is a mammoth 11 pages long. So welcome, Sir John. And now may I pass the virtual microphone to SMG Chair, Dame Mary Archer.
Thank you, Roger, and welcome everyone to this evening's event. I'm thrilled to be introducing my old Cambridge boss, Professor Sir John Meurig Thomas, to talk about his latest book, Architects of Structural Biology, which was published in February. The book's a fascinating account of what happened when physics collided with biology, with a good dollop of chemistry thrown in, and the technique of X-ray diffraction was painstakingly developed into a tool that revealed the structures of some of the most important molecules of life. If you saw the slides we showed just before we started, you'll have seen some of the spectacular objects now in our collection that were used to record X-ray diffractograms or to model the intricate three-dimensional structures they revealed. It's now my pleasure to hand over to John, who's going to show some slides as he talks to us about 4 of the great heroes of structural biology he knew so well and described so affectionately in his book. And then he and I will have a conversation about some of the issues it raises. So over to you, John.
I wrote this book about these 4 people because they were not only brilliant scientists, they were great, humane, and altruistic individuals. The one I knew best was one on the top right, which was Max Perutz. I knew him for 25 years. He lived a few doors away from me. We used to go for walks together. We used to exchange papers. He came to Cambridge in 1936. He was born in Vienna in 1914 because he wanted to solve a great problem in biochemistry. Now, below him is Dorothy Hodgkin. I first met her in 1974. I was asked to give a review lecture in the Royal Society. As soon as I finished, she sprang to her feet, congratulated me, and befriended me. She came and visited me in Aberystwyth, and she came frequently to the Royal Institution to listen to my and other people's discourses. She was born in Cairo in 1910. Mother was a very great Egyptologist. Now, John Kendry was one of the cleverest individuals I've ever met, mathematically, structurally, and astutely, and a wonderful organizer. He was a fellow of Peterhouse. I knew him for 10 years. He was born in Oxford, and he went to Clifton and did his initial degree in Trinity College, Cambridge. But in the jungles of Sri Lanka, he met a man named J.D. Bernal, whom I'm going to mention later, who told him, when you go back to Cambridge, forget your chemical kinetics. Go and look for Max Perutz and study biological materials. Right above is Lawrence Bragg. Now, unfortunately, although he was my predecessor but one, I met him only once, but I knew his 2 sons and his 2 daughters, and I read more than 200 of his papers and listened numerous lectures by him. Now, on the next slide, I want to show you a picture that I showed in an article that was invited by the editor of Nature in 1993. It's called The Architecture of the Invisible. Why do I show this? Well, X-rays were discovered accidentally in 1895. But by 1912 and 1913, nobody really knew what X-rays were made of. The man on the right, William Bragg, thought that they were corpuscles, like alpha particles that are liberated by uranium. The man in the middle, Max von Laue, is the man who carried out the experiment in 1913, which demonstrated, and I'll show it to you in a moment, beyond any doubt that X-rays were waves. And the young man on the left is the son of W.H. Bragg, 22-year-old Lawrence Bragg. Each of them became directors of the Royal Institution in due course. Now let me show you the next slide. Illustrates the experiment that Laue carried out. He took X-rays, he took some lead screens, and then he put a crystal of zinc sulfide. And what he discovered was quite sensational. On the photographic plate, he saw spots. The only way, if you look at the next slide, the only way in which you can interpret that is to assume that you have a phenomenon called diffraction. The word diffraction you can also use as interference. Those spot patterns demonstrate that the individual atoms in that crystal scatter the X-rays that come through. Now, he demonstrated very well that you could interpret the interatomic distances between those atoms using a rabbinically complicated method illustrated on the right-hand side. So complicated that others began to feel that there must have been other methods of interpreting them. And that's where Lawrence Bragg on the next slide comes in. You see, walking along the Backs one day in 1912 in Cambridge, he thought to himself, I really know what happens when X-rays impinge upon solids. They're partially reflected. Now you can see some of them being reflected upwards, but you can bring in that arrow of X-rays in another direction and they can be reflected in another direction. And from that, using this simple equation, it's called Bragg's law, n lambda equals 2d sine theta. You can see where theta is, it's a scattering angle. Now, the magical thing about this equation is that if you look at the fact that n lambda is a constant, 2d sine theta, therefore, also is a constant. And if sine theta is large, then d is small. That is the big secret that really tumbled upon the crystallographers of the early days. The next slide shows incredibly the way in which you get very large values of sine theta. It was J.D. Bernal and Dorothy Hodgkin in 1934 who pointed out that an enzyme called pepsin had spots going right out into what they call reciprocal space. Max Perutz did a similar thing with his hemoglobin. And that means, therefore, if you can interpret the real meaning of the intensities of these spots, it's what is known as Fourier transform. We needn't pursue that. That will tell you the structure. And you see, J.D. Bernal was so convinced that the riddle of life was contained in proteins. And these are both proteins, the hemoglobin and pepsin. On the next slide, you'll see an interesting example of how when you use the same, or rather the maximum quantity of diffraction spots that you get in reciprocal space. If you look at the 2.2 number on the top, it'll give you very poor resolution of the structure. If you go to 0.77, it gives you absolutely top-notching description of the structure of what is known as 4,5-diamino 2-chloropyrimidine. Now, let's go to the next slide, and you'll see also that what W.L. Bragg discovered was significantly different from what von Laue had done. Von Laue's picture was a simple cubic one, in which at each corner you have either zinc or sulfur. But W.L. Bragg found that his proper interpretation gave rise to a face-centered cubic. Now, I just include on the right a simple equation which relates the density of a solid to its molecular weight. That became very important in Dorothy Hodgkin's work when she joined J.D. Bernal in Cambridge. Now, the next slide is very important in that it shows the team that W.H. Bragg assembled in the Royal Institution in the 1920s and 30s. Bernal was absolutely incredible. According to Max Perutz, he said that Bernal had knowledge pouring out from him like water from a fountain, unself-consciously. He seemed to know everything. He was called sage. He solved the structure of graphite. His friend Asprey was the man who was told by Bragg to look at molecules of the living world: hair, wool, silk, fingernails, skin, etc. And he went to Leeds to complete his work there. And Bernal came back to Cambridge, to the Department of Mineralogy, would you believe it? Now, there are others like Robertson, who went to Glasgow, Cox, who came from Bristol, and the great Kathleen Lonsdale, who was the first lady to become a Fellow of the Royal Society. Now, on to the next slide. Here is an illustration of what we mean by a protein structure. You take an amino acid. Now, there are 450 naturally occurring amino acids, but only 20 of them are used in the processes of life. Now, when you combine one amino acid with another, water is liberated and you form a peptide bond. You form a dipeptide. Now, an enzyme like lysozyme, and I'll come back to this later, lysozyme is the enzyme that destroys the cell walls of bacteria. It has 129 amino acids. Now, I'm just showing you at the moment this linear structure of the amino acid, lysozyme. I'll come back to it shortly. On the next slide, I want to show you what the chemical composition of lysozyme is. You see, these three-letter acronyms, they're glycine, lysine, valine, alanine, etc. That's what they stand for. And you can see that there's one end which has got NH2 and the other which has got COOH. Now, this is the structure done chemically of lysozyme. The next slide shows the incredible work, very brief summary of it, that Bernal and his co-workers did in Cambridge in the Department of Mineralogy. With Dorothy, he looked at sex hormones, he looked at cholesterol, and he looked at androsterone and various other things. And Max and Van Kuchen looked at chymotrypsin and hemoglobin. Now, on the next slide, I want to show you how Dorothy looked like when she graduated in Cambridge in 1935. She adored Bernal, and she thought that Bernal also was one of the cleverest people that she'd ever met. In fact, he came to Somerville when she was an undergraduate, and he swept everybody off their feet by the genius of the man. Now, on the next slide, we want to show you a paper that the title of which, by Bragg, Kendrew, and Perutz, Polypeptide Chain Configurations in Crystalline Proteins. The big mystery in structural biology is, how do the amino acids form these polypeptides? And what is the nature of the bending and the folding and the misfolding of the polypeptides? Well, these three people published a paper in 1950, and it was demolished by this American, Linus Pauling. He wrote 7 papers in the Proceedings of the National Academy of Science in the following year. And you see on the next slide, this is Linus Pauling with what he called, and it's a very, very important structure, the alpha helix. Now, he did this by model building. He didn't prove absolutely in any experimental way that the alpha helix existed. In fact, he was ill in hospital in Oxford at the time when he came up with this idea. Now go to the next slide and you'll see, here's the myoglobin crystals. Here are the tremendously rich diffraction patterns, one of myoglobin and one of hemoglobin, one of them done by John Kendrew and one by Max Perutz. On the next slide, you will see something which really was sensational. It was shown in the Nobel Prize lecture that John Kendrew gave. On the top left, you see that triangle with a hole. That's the alpha helix looking down. And on the right, it's the alpha helix looking at it sideways. And in the middle, there's what is called the heme group, which contains iron and also attached to it an amino acid. I'll show you on the next slide. John Kendrew showed this picture to Max, and Max called it an intestinal monstrosity. Here's the heme group as a circle. Here it is on the right there. And on the next slide, I want to show you a slide that John showed in Harvard, and it swept the Harvard community off their feet. What he did was to show you in the first 2 columns on the left, the chemical analysis of the sequence of the amino acid, lysine, serine, histidine, etc. Then on the 3rd column, he shows what he saw by X-rays. In other words, he could read off the amino acids. This was a major breakthrough, and it was inevitable that he was going to win a Nobel Prize. On the next slide, I just now want to switch to the Davy Faraday Research Lab. Mary, you know, you worked there, and I did. It was a very, very happy place. And Lawrence Bragg, who's circled right in the middle, used to say, you don't need more than about 20 or 30 people, but they've all got to be happy, and they've all got to be enthused and doing worthwhile things. Now, there are others who have been circled. David Phillips is diagonally up on the right to Lawrence Bragg, and right up the top is Uli Arndt. And before him, also circled, is the general factotum, Bill Coates. Now, these people set about, especially D.C. Phillips and Uli Arndt, to really make a major breakthrough in enzymology. Let me take the next slide. Here is David Phillips giving a lecture. It is the beginning of what they call experimental enzymology. In 1965, he carried out this wonderful talk. 129 amino acids were descended from the ceiling of the Royal Institution, and they formed a little globule with a cavity, and that cavity, which is shown in the bottom left, not only it revealed the active site of the enzyme, it showed also the alpha helix. On the bottom right is the diffractometer, which D.C. Phillips and Uli Arndt designed and manufactured. It was a major breakthrough. Up until then, everybody used films. But after that, they started using diffractometers. And the molecule called N-acetyl-glucosamine is part of the bacteria that this enzyme breaks down. If you look at the next slide, here's the team that did the work. David Phillips is second but one on the right. And the lady in the front there is his research student, Louise Johnson, who later became Dame Louise, and who later became the David Phillips Professor at Oxford. These are the people, that's the structure. And it was an absolutely sensational day in 1965, celebrating the 50th anniversary of the winning of the Nobel Prize by W.L. Bragg. The next slide shows you one of the most marvelous articles I've ever read. I periodically look at it. David Phillips, who was a good friend of mine. Here's the article. It says the arrangement of the atoms in an enzyme molecule has been worked out for the first time. And this is the mechanism which Louise Johnson worked out in her PhD thesis. And that is an incredible story of how clever the work at the Royal Institution, a small group of people led by Lawrence Bragg. He had hired, by the way, Max Perutz and John Kendrew for 13 years as honorary readers. The next slide is the Nobel Prize meeting in Stockholm. I knew all of these except John Steinbeck, who is the second from the left. You see Maurice Wilkins, you see John Kendrew, you see Max, you see Francis Crick. And by the way, the moment he was told that he won the Nobel Prize, he immediately phoned J.D. Bernal. And on the extreme right is the egregious Jim Watson, who was very unkind to Rosalind Franklin. And by the way, Mary, you may remember that Rosalind Franklin graduated in the Department of Physical Chemistry in Cambridge. Now, in May of 1952, the next slide shows a visitor named Erwin Chargaff. John invited him to dinner in Peterhouse. And he met Watson and Crick for the first time because John had invited them to dinner. And this man was an extremely erudite Austro-Hungarian biochemist who'd fled from the Nazis and had gone to Columbia University. He said to these two men, namely Jim Watson and Francis Crick, "What are you working on?" And they said, "DNA. Did you read my paper?" "What paper?" "I have not heard the journal even." And then he described and said, "Look, every time, whenever you take DNA, adenine and thymine is 1-to-1, guanine and cytosine is 1-to-1. At that point, according to what John told me, Francis Crick wanted to go back to the laboratory. James Watson claimed that he knew that. In any case, it's a very interesting story, but he never really appreciated the skills or the contributions made by Watson and Crick. And now the next slide, I do want you to see something about these two marvelous individuals. I mean, their shared credo. The great advantage of X-ray analysis as a method of chemical structure analysis is its power to show some totally unexpected and surprising structure, and to do so with absolute certainty. Here's the hemoglobin of Max, and here's the vitamin B12 of Dorothy. The next slide is also an interesting one. In 1945, Dorothy solved the structure of penicillin. Now that makes it possible to manufacture penicillin, which is one of the main reasons why molecular biology is so important. These two men, Robinson and Cornforth, they both became Nobel Prize winners. They absolutely refused to believe that there was what is called a beta-lactam ring in the structure that Dorothy solved of penicillin. But she was right, and nobody can deny that. But the chemists, the organic chemists, really couldn't work that out themselves. Now, there's another slide I want to show you. The next one, please. Now, this is the tribute that Max paid to Dorothy at her memorial meeting in 1994. It's in my book, by the way. Margaret Thatcher was present there. She was a student at one time of Dorothy. She radiated love for chemistry, her family, her friends, her students, her crystals, and her college, to which she generously gave part of her Nobel Prize for the support of students and for the college staff. There was a magic about her. She had no enemies, not even among those whose scientific theories she demolished or whose political views she opposed. Just as her X-ray cameras bared the intrinsic beauty beneath the rough surface of things, so the warmth and gentleness of her approach to persons uncovered in everyone, even the most hardened scientific crook, some hidden kernel of goodness. It was marvelous to have her drop in on you in your lab, like spring. Dorothy will be remembered as a great chemist, a saintly, tolerant, and gentle lover of people, and a devoted protagonist of peace. Thank you.
And thank you, John, very much.
Oh, we can't hear you. We can't hear you.
Now, can you hear me?
Yes, we can.
Sorry about that. I think I unmuted myself before I was unmuted by Central Command. So, John, thank you so much for that fascinating talk, or should I say discourse, given that we're all in evening dress, at least from the waist up, in honor of the Royal Institution, where I was George Porter's postdoc before I came to Cambridge, which is where we met. You ended with that lovely tribute to Dorothy Hodgkin, paid by Max Perutz at her funeral. And I too knew Dorothy. I was a young Don filling in at Somerville in 1971. And Dorothy was very much the grande dame of the college. Very famous, of course, for her Nobel Prize, but more famous in Somerville, I have to say, by being the first serving fellow to have that remarkable thing, a baby, while working. And you also mentioned a couple of other ladies who I greatly admire, well, three actually: Kathleen Lonsdale, the great Kathleen Lonsdale, Rosalind Franklin, who read chemistry at Newnham, which I later taught at Newnham College, Cambridge, and Louise Johnson, who sadly I met in unfortunate circumstances when I was chair of Cambridge University Hospitals, and she came into Addenbrooke's, which is part of CUH, after she'd had a stroke. But I very much remember my conversations with her at that time. So, John, you've told us the stories of four great scientists: Lawrence Bragg, Max Perutz, Dorothy Hodgkin, and John Kendrew, and all of them you knew. All of them made extraordinary contributions to structural biology. But you yourself have made founding contributions to structural chemistry. Can you tell us a little bit about the key influences on your scientific career?
Well, it's because I mingled with metallurgists after I finished my PhD, and I learned a language which was spoken by people like Peter Hirsch, F.C. Frank in Bristol, Neville Mott in Bristol, and also Archie Howie in Cambridge, and also, even more so, Alan Cottrell. They talked about dislocations in solids, imperfections. And I thought to myself, when I got appointed in Bangor, that it was worthwhile investigating the chemical, physical, physiological, not physiological, photochemical, photophysical consequences of dislocations in solids. So that's really what I did for most of my life. I followed it up in Aberystwyth and also to some degree in the Royal Institution and again back in Cambridge. So that's the real reason why I did what I did. I did write a book on catalysis in 1967, and to my good fortune, it was published in Russian and it was used all over the Soviet Union as well as America. So I did get a bit of credit out of that. So that's my story, as it were.
Quite rightly, you got credit not only in Russia, but across the world for your own very distinguished career. Now, can I continue with a little challenge? You've shown us how X-ray crystallography developed and how it provided information not then obtainable in any other way about the beautiful three-dimensional structures of proteins, which are, of course, the key to their function. But given the recent development of cryo-electron microscopy, cryo-M for short, do you think X-ray crystallography has had its day?
I don't think it's had its day. I'll tell you why. First of all, these cryo-electron microscopes, there are about 150 in the world. They each cost £5 million. Cambridge has 8, London has about 4, Oxford has about 8. Some countries like Portugal, Spain, and the whole of Russia are without them. And the reason why X-rays will always be needed is because you want to look at small molecules that the pharmaceutical chemist, GlaxoSmithKline, will always have an X-ray crystallography machine to determine structures. But if you want to look at misfolding of proteins and to look at the real subtleties of what's going on in molecular biology, then you have to go to cryo-electron microscopy. And that is booming. It's expanding at a great rate. In fact, in LMB at the moment, most of the structures they send off to the protein data bank in Rutgers in America are all derived by cryo-electron microscopy. They don't use much of X-rays. So that's the short answer to your question.
Thank you. And am I right in thinking that another difference is that you don't need a crystal for cryo-M? And of course, X-ray crystallography, half of the hard work was actually making these awkward, unwieldy molecules crystallize in the first place.
Absolutely correct. You're absolutely right. The great thing about cryo-electron microscopy is that you can look at these big molecules in solution. You don't have to crystallize them. And that's why people like Richard Henderson and others are doing such marvelous work in that area.
I don't know if we got onto it in our film loop at the beginning, but Richard very kindly gave the Science Museum a very large Joyce Loebel scanner, which he used in his pioneering cryo-M work. So we're always on the lookout for good pieces of kit to put into the national collection. So you showed us very nicely in the case of lysozyme, John, that proteins are chemically quite simple structures. They're long chains of different sequences of those 20 vital amino acids. But of course, it's the way, as you said, that those long, slender strands fold, twist, and combine together to create complex three-dimensional biological molecules, largely, I think, stuck together by hydrogen bonds. That's the key to their function. Now, in chapters 9 and 10 of your book, you discuss some of the problems that arise when protein folding goes wrong. And perhaps you'd say a word about how that happens and what the consequences are.
Well, the consequences are very serious. I mean, Alzheimer's disease is one, Parkinson's disease is another, and there's another disease which is studied by a Peterhouse man, Tony Crowther, called Pick's disease, which affects the brains of people. So indeed, the big mystery is to try and be able to predict exactly what sequence of amino acids you can put together in such a way that the material that you end up with is benign and not in any way harmful for the human existence. I mean, as we grow older, it's been estimated that I think at the age of 80, something like 40% of the people might well have Alzheimer's disease in the future.
Yes, that's something to escape, very much so. So thank you. And of course, they are now getting much more of a handle, aren't they, on what may cause misfolding. It might be just a simple single amino acid is in the wrong place or is the wrong amino acid.
Indeed, well, you see, in the case of sickle cell anemia, it is only one amino acid replacement that causes the hemoglobin blood to form sickles and to give you terrible diseases. Yeah, absolutely. John Kendrew thought, and he made it public in the Nobel lecture, that there would come a time when you would be able to predict exactly what sequence you could have, but that's still a long way away.
It is indeed. Of course, you mentioned both hemoglobin and myoglobin. And am I right in thinking that myoglobin is kind of about a quarter of hemoglobin?
That's right.
It has a different function.
Yeah, it's got 2,000 atoms, and the molecular weight of hemoglobin is 6,800. So, I mean, one is a quarter of the size of the other.
Which is, I think, why John Kendrew decided to go for myoglobin rather than hemoglobin, which Max had, well, not appropriated, but he persevered with.
Yeah. Well, I mean, they had a good relationship with one another, and they were very generous to one another when they spoke about one another's work. You know, there was some tension between them, but I mean, and undoubtedly, Max was deeply depressed when he saw that myoglobin had been solved, because he wondered, you know, is this going to be the end of his story? Fortunately, 3 or 4 years later, he solved the hemoglobin structure.
Terrific. Now, John, you're clearly very sensitive to the genius of place, whether it's Michael Faraday at the Royal Institution, where you were director, or Peterhouse at Cambridge, where you were master, and where at one time, you tell us in your book, there were no fewer than 4 Nobel laureates in structural biology in the fellowship. Now, in these socially distanced times, what would you say about the importance of face-to-face interaction in research?
I think it's absolutely invaluable. You know, when I came to Cambridge, I didn't realize until I came how fortunate it was for students and members of staff in colleges in Oxbridge to mingle with one another and to be taught even in informal environments like at lunch and at coffee, but also to have interaction with top-notching people who really put them through their tasks. I think it's absolutely invaluable. And I think you've benefited, for sure, from your teaching and from your learning in that kind of way at Newnham, Trinity, and other places.
Yes, it's a huge privilege, I think, to live the collegiate life. But actually, do you know, it was at the Royal Institution where I first got switched on to the importance of what we would now call public engagement with science. And it was watching those wonderful discourses, which you've mentioned. George, of course, gave many great discourses. And actually, when I gave my first one, he very kindly and nobly stood in for Bill Coates and was my lecture assistant, which was fun for, I think, everyone. And I remember, again, you know, great range of things. I remember Ninette de Valois talking about, as it were, the joints of ballet dancers. And she had a young ballerina on the lecture desk, you know, doing pirouettes and things. It was amazing. And we had somebody make synthetic diamonds. We had all sorts. So I think, you know, the Royals Institution, the great theatre of science, is a very good stable to come from. So anyway, enough about place. What about people? So all the scientists you describe in your book were internationalists with European friends and connections, particularly, of course, Max Perutz with his Austrian background. An interesting fact I learned about Max from your book again was that he was the Austrian downhill skiing champion in his youth. That was before, of course, he left Austria, came to Cambridge, and before we, the Brits, briefly interned him in Newfoundland at the start of the Second World War as a possible enemy alien, though he never held it against us. So what are your views, John, about future frameworks for international collaboration in a post-Brexit world?
Well, I'm somewhat depressed, Mary, because, you know, when you think of Max and John Kendrew, they both spoke 4 European languages. They went out of the way to set up the European Molecular Biology Laboratory in Heidelberg, which is now a major place of research, and also offshoots of it in Hamburg, where they have a synchrotron, in Grenoble, where they have a neutron source. I'm hoping that new ventures can be worked out, but I'm rather depressed by the idea that many of the schemes that have been going so well are now being threatened because of what we've done over Brexit. I hope I'm wrong.
Well, scientists have always been very good, haven't they, at ignoring geopolitical tensions and boundaries. And let's hope that continues to be the case.
Yeah.
I will remember the first foreign trip I made. It was because George was too busy to accept an invitation, so he sent me off, and it was to Bulgaria, and it was, you know, the Cold War was raging, and there were a few kind of heavy kind of security types in the back of the lecture theatre who must have been extremely bored by the proceedings. But, you know, the scientists, they mingled quite freely. I guess it depends what line of research you're in, though.
Yes, indeed.
We weren't on the Manhattan Project trying to make a bomb. We were doing something more peaceful. Anyway, so science is a great international endeavor, and I think one of the exciting things about it is even if you only discover one thing, you have put one little brick into that great temple of knowledge. Richard Feynman once defined scientific progress as imagination in a straitjacket. I wonder what you think he meant by that. At the Science Museum, we absolutely repudiate the notion that science is not a creative activity. What do you think the role of creativity in science?
I'm very clear on this, and so was Max, you know. I think I mentioned to you before, Mary, that when I wrote his obituary in the Times, I quoted the fact that Max, when he was asked, why is it and how is it that you've made the LMB such an incredibly successful place? Some people would argue that the LMB is one of the greatest scientific research establishments ever created. The head of medical science in Stanford believes that. He would say, look, take your mind back to 15th century Florence. Think of all the men who were there: Brunelleschi, Donatello, Botticelli, Masaccio, etc., etc. How did these people come together? Well, they were given incredible freedom. Now, what Max used to say and emphasize, in the LMB, he would recruit top-notching people, absolutely top-notching people. He would then say to them, do whatever you wish. Get onto a problem that you feel is important. Then make use of the workshop facilities in the place. He engineered a way of making it so easy for people who were working at LMB to carry out magnificent work, which they would never have been able to carry out elsewhere. So he says, look, creativity cannot really be engineered. It turns up like puck in unusual corners. And I end my story on that.
Well, thank you, John. You mentioned the LMB several times, the great laboratory of molecular biology, and I also sort of have a link with it. Not that I ever worked there, of course, but when I was chair of Addenbrooke's CUH, Cambridge University Hospitals, it was the time when the old LMB, which is at the front entrance of Addenbrooke's, was trying to get the funding and, more importantly, actually, local authority planning consent to build its magnificent new laboratory of molecular biology in what was then just come out of the Greenbelt and is now part of the Cambridge Biomedical Campus. And I well remember talking to Sir Colin Blakemore, who was, I think, then director of the MRC, about how this move was to be achieved. And it's a wonderful laboratory in which they haven't lost that importance of physical interaction and interdisciplinary approach. So thank you, John. Thank you for your talk. Thank you for sharing with us your stories of the creativity of 4 of the greatest scientists of the 20th century. And I'm only sorry that we must now draw this conversation to a close.
Thank you, Mary. Thank you very much.
So I'd like to thank everyone who's joined us this evening and the Science Museum staff who've supported us behind the scenes. And I'm now going to hand over to Nicholas Spindler, who's head of philanthropy at the museum, for a final word.
Thank you, Mary, and a huge thank you to you and Sir John for such a fascinating conversation and for bringing to life not only structural biology, but the personalities and people behind the science. If you put a museum under a microscope or an X-ray diffractometer, you'll see that it's made up of objects, exhibitions and galleries, but mainly and most importantly, people, from our chair to our curators, to our visitors, friends, supporters, and our patrons. And I know that many of them are in tonight's audience, so I just wanted to take the opportunity to say a huge thank you to all of you. Your ongoing success is the lifeblood of the Science Museum Group and vital, more vital now than it ever has been before. It's really thanks to your support that we've been able to keep producing events like this during lockdown and beyond, and hosting such luminaries such as John Meurig Thomas. So thank you. If you're interested in finding out more about the Patrons Programme and the events that we have coming up in the future, or would like to sign up to become a patron, please do get in touch and more information will be sent after in the follow-up to this event as well. There will be also a recording if you'd like to rewatch this event or share it with your friends and family too. So I just want to say again, thank you to Dame Mary, to Sir John, and to everyone for joining us this evening. Have a wonderful evening.